This video is part of a series focused on developing plugins for MicroDrop. If you haven't already, I would recommend watching the first video in the series, which shows the setup required to test development plugins with a release version of MicroDrop. In this video, we're going to be looking at specifically a plugin that connects to DropBot hardware signals. So we're going to look at several signals that are logged, including capacitance-updated messages, channels-updated messages, so the actuated channels have changed, a chip being inserted, a chip being removed, and the DropBot connection being established or lost. The implementation of this plugin is in the init file, and this plugin is posted in the Sci-Bots organization on GitHub under microdrop.dropbot-signals-plugin. I'll provide a link in the description, and I'll also provide a link to the first video in the series. The implementation again is under this init file, and what this plugin does is when a step is executed in a protocol in MicroDrop, it attempts to look up the DropBot plugin if it is currently installed, and if it can successfully find the DropBot plugin, then it creates a reference to the corresponding DropBot signals to use locally. If any of this fails, then the step will just be marked as completed and the message will be logged indicating the DropBot plugin wasn't found. Otherwise, the idea is that we will connect to all of these signals and simply log a message indicating that the signal has occurred. So the rest of the implementation of this method is a series of callback coroutines. So you notice that it's an asyncio coroutine. So we have one for the on channels updated, we have one for on inserted, on removed, on DropBot connected, and on DropBot disconnected. Now all of these are simply logging a message. The on channels updated is doing a little bit of calculation here just to get a reference to the currently loaded device file, and then get the actuated electrodes. So given the channels that are actuated, which are the corresponding electrodes? And then given those electrodes, then look up the areas of those electrodes to find out the total actuated area combined. And then just log out a message that displays that in a pretty way. So the list of actuated channels as well as the total actuated area. Now, if we look at the on capacitance updated callback, it's a special case. And the reason is that the capacitance update messages arrive in as little as 10 millisecond intervals. And so if we were to log every message, the console would just be full of log messages and create a backlog. So this implementation demonstrates how we can avoid issues like that backlog by putting a rate restriction on this callback. And we can do that using the debounce library and the debounce class. What it does is it creates a wrapper around whatever function you specify, but then you can specify the maximum rate that you can receive these messages. So here we will only call this callback at most every 2 seconds. And you can look at the implementation of the debounce library to get more details, but the main thing here is that you can set a a maximum wait that you need to wait before you call the callback. So this allows us to not call this for every capacitance updated message, but only call it at a maximum of every 2 seconds. The next step is to define the mapping between each signal name and its corresponding callback function. And then we will call on this DropBot signals instance, which we got from the plugin, the DropBot plugin up here. And for reference, this is the DropBot plugin has this DropBot signals attribute, which is a blinker signals namespace. I'll provide a link in the description of the video to the blinker package for more information. But here, for now, we'll just assume that you know what a blinker namespace is. We iterate through this mapping from the signal name to the corresponding callbacks, and then we just register each signal with the corresponding signal of that name on the DropBot signals namespace and connect that callback. And then, so for the duration of this function call, those callbacks are connected. Once this function exits, those callbacks are automatically disconnected from the DropBot namespace. So if we weren't doing anything in this function, if we weren't doing anything else, then we wouldn't actually see any of these logging messages, because the function would exit immediately and those signals would be disconnected. However, the more likely scenario is that you're going to be doing some kind of work. So you may connect those signals, and then you may want to wait for the actuation duration, or you may want to log the capacitance values or do some interaction with the DropBot while you're monitoring those values or something. But the main thing is that once this function exits, you will lose these callbacks, which is probably what we want, and in this case our implementation relies on that, because on the next step these callbacks will be registered again, and in that case we don't want the callbacks being called twice for every signal. So that is the desired behavior, but it may be unexpected if you weren't thinking that that's how it worked. And lastly, this is something that's specific to we're using async I/O capabilities, but we're currently stuck with Python 2.7 because MicroDrop is using GTK2 on Windows, for which we only have an implementation for Python 2.7. And so to get async I/O functionality, we're using the trollius package, which requires different syntax than Python 3's async I/O syntax. But here, so we get yield, and then the trollius is renamed to async I/O .from, and then in this case we're just sleeping for the duration specified in the electrode controller plugin. So this is in the protocol table. You'll see the duration seconds. So we're just accessing that value from the plugin keyword arguments, and that's what was passed into the onStep_run function. So we can look up values from other plugins if we need to in the plugin keyword arguments. And then in this case, we're just looking at that duration. We're going to sleep for that duration, which means that these callbacks will continue logging until this sleep duration is complete. Okay, so let's change into our MicroDrop development plugins directory that we created in the according to the first video's instructions. And we look under here, we've got our minimal example plugin that we already had from the first video. And now we can clone this repository. So copy that link, git clone, and the one trick here is that we need to clone it to directory name that is a valid Python module so that it can be imported by MicroDrop. So I will rename it to MicroDrop signals underscore plugin. And note that it's underscores between these words, so it's a valid Python module name. If we switch into here, you can see this is the same as this repository here. Now, if we launch MicroDrop, we'll just wait for it to load. I'll connect to the DropBot. So the DropBot plugin is enabled. We don't have a chip inserted right now. I will insert a chip. I've just inserted the test chip, for example, and we'll turn on some electrodes. Actually, let's turn on 1, then 2, then 3, and we should be able to see the value going up on subsequent steps. So we'll set the duration to, say, 3 seconds so we get at least one update. Now, if we look, all of the messages are being logged to the debug level, so we want to make sure that under options, your log level and the file debug level, or the file log level, are both set to debug. In this case, they already were. Then we'll go to our first step, and we'll press play, and now go look over here. It might be difficult to see while this is running, but we'll go back and we'll look at the log afterwards here. Okay, so the experiment has completed, protocol has finished running, and now we'll go back and look for our messages. I forgot to do a step here, which is we need to enable our plugin. So that's under File, Plugin Manager, enable our plugin, and now we'll try to run it again. So there we can, I already saw a message there, but we'll wait till it finishes. Okay. So here's a DropBot signals plugin message. So on channels updated, 8, 13, and 8 were turned on with the area. And we should also be able to see, yes, the DropBot signals plugin here, DropBot capacitance reading received, 33 picofarads at the actuation voltage. And so this video demonstrated how we can take the DropBot signals plugin and enable it in MicroDrop to log out these different messages. But you could be doing anything under these, and that could include writing some capacitance values to a file, or using capacitance values to then do custom actuation of the DropBot. So if you were, for example, using a pump to fill up a reservoir, you could monitor the capacitance values and then change the actuated channels once the capacitance has reached a certain value, and continue the protocol after that. So this should provide a way to connect to the DropBot signals as required.